Hey y'all, it's Mr. Boyden back at it again, and today we're going to be talking about the dot product of vectors. Why are we doing that? Because it would be really nice if there was a way to find the magnitude of vectors and the angle between vectors quickly, and this is going to do that. We did learn in the last unit that we could use the laws of sines and cosines to find angles inside a triangle, and this is going to be really similar to that today, although I hope that you'll see that with the dot product, it's actually a little bit easier to use vectors than it is to use basic triangles. So basic things I want you to know at the outset. I'm calling this the dot product. Many texts call it the dot product. Some texts will call it the scalar product. And that is the exact same thing, okay? Those are synonymous. The dot product is a type of multiplication with vectors. There is another type called a cross product, which we actually don't teach in IB at this time. So you don't have to worry about doing it, but the cross product symbol is a cross and the dot product symbol is a dot. And that's why, guys, I'm not going to be saying like vector B times vector A, because there's two different types of multiplication, so we have to be specific. So that's a habit, especially for those of you if you're going to go on in any sort of math, science, engineering field. We want to make sure you don't have a bad habit with thinking there's just one kind of multiplication. So with that said, let's see what a dot product is. Let's see how we do it. So here it is. Here's the definition, okay, right here. So u dot v, and that's how we say it. Remember, we're not going to say times. U dot v, and then here's the information. But what I would want you to know that means is that this is where we take the x component of the vectors and multiply them together, and this is where we take the y component of the vectors and multiply them together. And if we had the z components of the vector, we would also multiply them together here, and then we add all those results. So let's do an example. I'm going to take the x components, 3 times 1, that's 3, and 2 times negative 3, that's negative 6, and 3 minus 6 is negative 3. That's a dot product. And do they get harder? I mean, I guess the numbers could be bigger, but not really. The process doesn't get harder than this, okay? So one thing that you should know is that the dot product produces a scalar, and a scalar is just a number. So any dot product will always produce a number. Sometimes people think, oh, you know, a vector times a vector is a vector. But it's not really times, it's dot, and so that's going to produce a number or a scalar. Okay, so be careful of that. That's something that some students mistake early in the learning here. Let's try another example. If you already feel like you've got this down, you could try pausing the video and see if you can do it on your own. Then when you're ready, hit play and see how you did. Let's do u dot u, which means we're going to dot u. Oh, actually, that's a typo. U dot v is what that should say. So we'll do u dot v. So all I'm going to do is take the first components, 3 times 2, we know that's 6. Negative 1 times negative 4, we know that's 4. And 2 times 0, we know that's 0. So we find each of those, we add them together, and we get 10. Now let's do v dot u. So we're going to take the v component, 2 times 3, and notice that's still 6. Okay, we're going to take negative 4 times negative 1, that's still 4. And 0 times 2 is still 0. Okay, so what I'm trying to show you with these two examples is that the dot product is commutative. The order doesn't matter. Okay, and that means that we don't have to stress about, wait, what if the order is different? It doesn't matter. Okay, now let's actually do u dot u, u times itself. So what do we do? That would be like if there was another vector u right here, and we're going to multiply it by ourselves. So 3 times 3, that would be 9. And negative 1 times negative 1 would be 1. And 2 times 2 would be 4. We add the results together, and we get 14. Now remember this set of symbols? That's asking for the magnitude. So be careful. And the way I taught you that is to square them, to add them, and to root them. So let's square each of the components. That becomes 3 squared is 9, and 1 squared is 1, and 2 squared is 4. Square them, add them, root them. Hey, that's the same thing as this, isn't it? So that's the square root of 14. So some people will say, and that's why I'm showing these two together, some people will say that the dot product is actually a shortcut for finding the magnitude. My personal opinion, I don't agree. I think square them, add them, root them is every bit as easy and quicker. So I don't subscribe to this belief that that's the best way to do it, but if it works best for you, then you should do it. Okay? Let's do this last one. And this is where some people get a little bit confused because some people want to distribute this u. The problem is, if we distribute this u into here, is it a dot product or a cross product or something different? We actually don't have that information, which is an indication that we cannot distribute this u in. What we can do, though, we can do the dot product from the outset. And we already know from part A that u dot v is 10, so that now says 10u. And some people get a little bit confused at this point because they say, wait a minute, there's no dot there. So is that a dot product? Is that a cross product? Is it something different? So you only need to define the operation when it's a vector times a vector. But right now, this is a number times a vector. It's 10 times u. So all we do is we take the u vector and we multiply it by 10. So that would be 30 negative 10, and 20. And some people say, but wait, Mr. Boyden, you taught us that when you multiply, you get a scalar, you get a number. But remember, that's when we have a dot product. A dot product meaning a vector times a vector. That produces a scalar. Down here in this question, that's not what we had. We had a number, or scalar, times a vector, and that does produce a vector. And so here's what it's really useful for, okay? It's how we find an angle between two vectors. Things I would want you to know about this, and yes, you need to write this down in your notes, is that it only applies to vectors that are arranged what I call tail to tail, or initial point, where the initial points are lined up, and it's finding that angle right there. I also want you to notice in this rule right here, this looks exactly the same as the version we learned of the law of cosines, because essentially it is the law of cosines, we're just doing it with vector shortcuts. So write this down, then we're going to do an example of how to solve it. First thing I want you to know, if we were going to do this question, we notice it says cosine theta, so the first thing we would always type in our calculator is cosine inverse. Then, we're going to go find the dot product of the two vectors in question. Here we're given two vectors. And I've intentionally written them in a different form so that we can learn something new and maybe be a little bit challenged. If it's i's, j's, and k's, a linear combination form, all we need to do is line up the i's, so 2 times negative 4 is negative 8. And we line up the j's, so that's a j, and that's a 2j. Now notice that's negative 1 times 2, so that's minus 2. And then there are no k's here. So that would be 0 times negative 1, which is 0, so I don't even have to write it. Then we're going to go get the magnitudes of the vectors. Square them, add them, root them. Guys, if you need to write out the work, that's fine, but 2 squared is 4, and 1 squared is 1, and 4 plus 1 is 5, so that's root 5. And I'll come over to this one, and 4 squared is 16, plus 4 more is 20, plus another one is 21. And so all I have to do then is I can go straight to the calculator. And that's why I say this is kind of a quick, nice little shortcut. So I'm going to take a moment here and type that in. The square root of 5 and square root of 21 and 167 point. Well, we'll round to 3 significant figures. That's what I'd be like. So we'll do 167 degrees. Now, that's pretty useful when you consider it's really hard to visualize a vector in 3 dimensions. We did one earlier in the video series where we had a vector here and a vector there, and we found this angle and we found that angle and added them together. That worked great for 2-dimensional vectors, but when we're dealing with 3-dimensional vectors, it's notoriously difficult to visualize. So this is a short, easy trick that allows us to find those easily. Let's do another one. In my mind, it's time for you to pause the video and try this one on your own. This is actually a little bit easier an example than one we just did, and it'll give you an idea of where you are in your learning right now. So here I go. Cosine inverse. I need the dot product on top. Dot product is where I take 3 times negative 1, so negative 3, and where I take 9 times 6, so plus 54. I then need to find the magnitudes, so square them, add them, root them. I like to write it out like this, 9 and 81 and adding them, that would be root 90. And then we'll square them, add them, root them here. That looks like root 37. And calculator time. So guys, I hope you see that this can be pretty darn quick. And maybe you need a little bit more time than I'm taking to figure out the different components we're typing in. But recall, the dot product was pretty simple. It's not going to take you very long. I mean, maybe it takes you twice as long as it took me, but that's not very long to do a question that is, you know, dealing with finding angles like this. So let me get this typed in here real quick. And I get 27.9 degrees. And that's it. That's all it asks for. One more thing we got to talk about today, so one more concept and one more example. A common question that will be asked, and this is whether you're doing physics or IB or AP, it doesn't really matter. It's going to come up all over the place. We're going to be asked some question about perpendicular vectors. So I want to talk about what that means. We already know that perpendicular means that vectors are making a right angle, which means that over here, we know that theta is 90. So let's write that out and see what happens. Cosine of 90 equals v dot w over magnitude v and magnitude w. And so we say, wait a minute, do we know what cosine of 90 means? Well, sure, we know that 90 is right here. What's the cosine value right there? Since it's x, that's 0. So 0 equals v dot w over magnitude v times magnitude w. And then we stop and say, all right, well, this is a fraction, and the fraction is equal to 0. So what can we know about the fraction? Well, we should remember that any fraction which has a value of 0 has a numerator which is 0. So v dot w is 0, and the numerator and the denominator is not 0. Now, it turns out that's not going to be a problem here because unless we're given 0 vectors, which almost never will happen, it almost never will be the case that we have a 0 denominator on this. Okay, but what we're going to look at is anytime you see the word perpendicular, you automatically need to think, boom, the dot product is 0. That's the quick shortcut for those questions. It is a prototypical question that will always be asked on a test, so you want to look out for this in a big way. Let's do an example so we can see what type of question we would be expected to do. Okay, pause the video and write it down. If you want to try it, you can. If not, just follow along. Looks like I'm given 2 vectors, given in 3 dimensions. They threw in a variable to see if I would trip on it. What value of r makes the vectors a and b perpendicular? I say, wait a minute, dot product must equal 0. And now I have a formula that I can easily fill in. So what I'm going to do is I'm going to go find the dot product. 3 times 8 is 24, and 2 times negative 4 is minus 8, and 2 times 2r is 4r, and right here it says equals 0, so I'm going to do that as well. And let's see, 24 minus 8 is 16, so I have 16 plus 4r equals 0. I'm going to move the 16 to the other side, so 4r equals negative 16. Let's divide by 4, so we get r equals negative 4. So y'all, we've already answered the question, okay? And if we had to do this like intuitively or visually, I think it would be pretty hard to figure out in 3 dimensions what would make these 2 vectors perpendicular. But this is a short, easy, quick way. I mean, look, that's like an Algebra 1 level equation. We're talking like 8th grade level math here once we recognize that the dot product has to be 0. So what we would claim is this is like our pre-calculus skill is the recognition of the process. The actual process itself is something we could go teach to middle schoolers they'd be able to do, which means this is something we can be really, really successful at. Now you're going to notice I've already written this, the dot product equals 0 and circled perpendicular twice in this video. And the reason I'm doing that is because my teaching experience tells me this is something a lot of students forget. They get stressed out, they get onto a test, and they don't remember when they see the word perpendicular that they need to just set the dot product equals 0, and then it's very sad because they don't score well. So please write something in your notes as you go back. So as you go back and study, you'll be reminded, oh yeah, these are super easy, and I got this, and I'm gonna get this right, okay? That's all for today's video. Hope you enjoyed it, and we'll see you next time.